All right, in this lesson we're going to begin our study of rational numbers. So I'm going to start off with a technical definition of what a rational number is. It is a number that can be written in the form of a over b. Let me put this fraction bar there, where a and b are integers and b is not equal to 0. So remember, going back to our number sets, we have our natural numbers, which are what we learn to count with, our whole numbers, which introduces 0 to that, then our integers, which have negative numbers. So now we've got any number that can be written as a over b where they're integers. So they can be negative, they can be any of our counting numbers or our natural numbers, and they can be our whole numbers, except for b. It can't be 0, and the reason is we can't divide by 0, which we'll discuss why that's the case later in this lesson. So we went over some examples at the beginning of the class, a few lessons back, but I want to go and give you some more examples here. We could have something like 3 over 5. That's a rational number. You can have negative numbers like negative 5 over 2. And so we learn in elementary school that we can take a fraction and make it a decimal by dividing it out. So something like this will divide out to negative 2.5. And so that's negative 2.5 is rational because it can be written as a fraction like that. Negative 5 over 2 or 5 over negative 2 would both give you negative 2.5. So therefore, negative 2.5 is a rational number. Our whole numbers, our integers, our natural numbers are also all rational because even a number like 3, it can be written as 6 over 2. Notice 6 and 2 are both integers, and so because 3 can be written as a fraction, it is a rational number. It can actually be written several ways. You could say 3 over 1. You could say 18 over 6. There's lots of ways you could show that 3 is a rational number. So we can have other ones like 0.3 repeating. Just because a decimal goes on forever, if we were to write this out, we'd go 0.333 and so forth. It just goes on forever like that. Because it's non-terminating, it goes on forever, does not mean it's irrational. It's still a rational number because 0.3 repeating can be written as 1 over 3. So what are some numbers that are not rational? The two most common examples we give are pi, because pi is non-repeating and it's also non-terminating. So you get 3.14 is what a lot of times you use in high school geometry for pi. But remember, pi goes on forever. It goes 3.14159 and so forth. But more important than it going on forever or not repeating, it can't be written as a fraction. There's no two integers I can write one over the other that when I divide it out, it gives me exactly pi. And so the Egyptians, as I discussed before, the Egyptians used 22 over 7. If you divide 7 into 22, you get something like 3.1428. Really close to pi, but not exactly equal to pi. That's what the Egyptians would use, and it worked for their purposes. Another good example for irrational numbers that comes up frequently is the square root of 2. The square root of 2 is close to 1.412135, blah, 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 blah. It keeps going there. There's no two numbers, no two integers that I can put one over the other, a over b, so that it comes out to be exactly the square root of 2. So those are two common irrational numbers you'll see, but everything we're talking about today is going to be a rational number. Two integers, one written over the other, where the bottom number there is not 0. So there are a couple ways that we can represent rational numbers, and the first we're going to look at is a set model. Now, a set model is a great way to introduce rational numbers to students seeing it for the first time because it's going to be a concrete model. Anything that's tactile that they can touch and manipulate, that's going to be considered a set model. One popular way that this is shown is with color chips. So you might give them something with some blank circles on it, and let's say we want to say represent 1/6, then you could draw out 6 circles like this and then use the counter chips to physically move those chips into a spot to show 1/6 or 1 out of 6. And that's really the key idea behind a fraction, is you're taking a whole and you're dividing up into parts. And so if we're looking at a rational number a over b, b is how many parts we divided the whole up into, and a is how many of those parts that you have present. So in this case, we had 6 parts. That's the total sum of all my chips there. And then I've got 1 chip colored. So you've got 1 out of 6 color there, or 1/6. That's one way you can represent it. I like showing it with Cuisenaire rods. I think it's a great way to introduce fractions, especially when we start to talk about adding and multiplying and dividing fractions. So let's take a look at how we would do that. So with Cuisenaire rods, we use these numbers. I don't use these numbers with fractions when we start talking about Cuisenaire rods. So I'm going to take those off by clicking on the numbers right there. And really, what I want to know is, what is 1 whole equal to when we talk about fractions? So if I use this as 1 whole, then what would be, what can I divide that into? So if I use the green bars will not divide into the orange bar equally. So I'm not going to use the green bars with that. Let's go a little bit smaller and use the yellow ones. The yellow ones will divide into it evenly. So now I can say that if 1 orange bar is a whole, then a yellow bar goes into it twice. So each yellow bar is 1 out of 2 parts there, or 1/2. So I can represent 1/2 like that. You can also represent 1/2 with something like this, like a red bar. And you can present that to a student and say, tell me what 1/2 of a red bar is. Then one of the white pieces there, or gray, whatever color your set has there for the 1 cube, is 1/2 of the red. So I think, maybe start off with counter chips or something else and then build up to this point, because now we can say, what about 3/5? So how would you represent 3/5? Well, the student first has to define what a whole is, and then divide that into fifths. So using the red bar, let's see if that goes into it 5 times. There we go. We've got 1, 2, 3, 4, 5. So we're dividing that length up into 5 pieces, and then 3/5 could be represented by saying if the orange is 1 whole, then 3 reds is 3/5 of that orange. So something very similar to using Cuisenaire rods is fraction strips, and I've got a copy of this in our weekly resources if you want to check that out. And so fraction strips, what I like to do is print something out like this, and you can do it several ways. I like to print out one and laminate it, and then that way students can shade them. But I also like to print them out and maybe laminate them and then cut them into strips. And of course you can buy these as magnets on Amazon and those sorts of things. So if you want a large display magnet up on your board, you can do that. And smaller ones for students to work on at their desk. This is also great for comparing fractions that we'll talk about later on in this video as well. So for instance, if I went to look at 1/2, we've defined 1 whole to be whatever the length of this is. And so 1/2 fits into this. We're dividing that whole into 2 equal parts. And if I ask someone to shade 1/2, we can shade in 1/2 like this. And so if you were in my class at the brick and mortar school, I'd have this out so you could shade it with maybe an Expo marker on a laminated piece of paper. But you can do that at home as well, printing out the sheet and shading it in as you practice. And then what else would be equivalent to 1/2? We could look at this and say, if I were to divide that whole up into 4ths, or 4 equal parts, I could shade 1, 2 of those. And this is a great way for students to visually see that 1/2 is equivalent to 1/4. It also allows them to see I can't take fifths and make it equal to 1/2 because this doesn't go, a fifth will not go into a half evenly. But if we look at 6, we can say that 1/6, 2/6, 3/6 is the same as 1/2. Same thing with 8ths, same thing with 10ths. And with 12ths, we could get 6/12, which is equal to a half. And then you could even talk and say, the pattern here is obviously we're going every other bar we can make 1/2 with whatever equal amount of parts we're dividing that whole into. And it's the even denominators that allow us to do 1/2. The odd denominators don't allow us to do that. You could do this as well as with 2/3. You could say what's equal to 2/3. Well, we've divided into thirds. There's 1/3, there's 2/3, and then we could do the same thing with 6. We could say, if you were to draw a line straight down through this, where a third meets, then you could see that we could do it with ninths right here, and we could do it with sixths right here, and we could do it with twelfths right here. We can make 2/3 with those and count those. 1, 2, 3, 4, 5, 6, 7, 8 twelfths is the same thing as 2/3. So all of these are nice tactile representations. This, if you're having them draw on it, isn't quite considered a tactile type thing because they're drawing and shading in areas. But if you're using the Cuisinart rods, if you're using the counter chips, or even if you take these and cut them out and make them move them around, they're physically moving something to represent fractions. And so that's where we get our set model or a concrete model for those things. The other way we could do it is with area. So you could, now that we're having them shade in things, we're going to consider this the area model. And so for instance, if you take a square and define that as a whole and divide it up into 9 equal parts, now you could say, what is 4/9 equal to? And you could say, okay, I've got 1, 2, 3, 4/9. And you could also discuss with this, is this the same as 4/9 like this? And so you can start to have them compare things with area. And I'll give you some homework with that later on this week, where you start shading in blocks to represent area and comparing those things. It doesn't have to be a square, it could be any area really, but usually we stick with rectangles and circles. I like circles because I like to talk about pizza. And so you can say this is, you eat half a pizza and your friend eats 1/4 of a pizza. How much total pizza did you eat, when you're talking about addition of fractions and things like that. So I think that using the circle slices kind of gets them interested. I know it sounds silly, just pizza itself, but it gives a story, and it also gives a little bit of a background of why we need to start talking about fractions. So we'll discuss the area model more when we begin adding and subtracting fractions. The next thing we're going to look at is the number line model. So this is moving forward a little bit more advanced in a student's understanding of rational numbers. So the number line model is, once again, you're going to define what a whole is. You could say that from 0 to 10 is one whole. What is half of that? And so we'd represent 5 right here as halfway to 10. But I could ask you things like, show me where 1/3 is. And so you'd have to break this up into thirds. I'd probably give you something a little bit easier, something that's divisible by 3. Like I might say that this is 12, show me where 1/3 is. And so we're going to break this space here from 0 to 12 up into 3 equal parts by making 2 lines. And so right here at 4, this is where 1/3 would be. And that would be 8, so you're going 1, 2, 3 equal parts is what we're dividing 12 up into. So these do get a little more challenging, and we're going to see that in a second after we get past these problems right here. We're going to start putting all of these fractions onto a number line, and then we're going to start saying if from here to here is 2/3, find the value of x. I'm going to work you through those in just a moment, but I want to talk about comparing fractions first. So the next thing is that we're going to look at is saying, what is larger, 4/5 or 4/7? And this says use some diagrams to determine which part is larger. So this is where I do like to look at the area model. Whoops. And so I just kind of draw a rough drawing of what 4/5 would look like, and I'm going to use a circle. And so if I took this circle and divide it up into 5 equal parts, and this one I'm going to divide into 7 equal parts. So pretend like those parts are actually equal on the 7ths there. And now if we shade in 4 of them, 1, 2, 3, 4 over here, and shade in 4 parts over here, I can see that 4/5 is larger just by comparing what is left over. So if you're telling the pizza story here, you can say, I ate this much pizza in green, how much is left over? Somebody else ate this much, how much is left over? If you were really hungry and you came to this party, which pizza would you go for? The 3 slices here or the 1 slice there? You could say these 3 slices. So, because that has more pizza to it. So this is a smaller fraction, or the green portion right here is a smaller amount compared to the green portion over here. And if you're like, well, maybe you drew these not quite equal, you could go to our digital manipulative site that I shared with you. Now, remember, this is in our resources for week 1. Let me pull that back up. And it's the NLVM website. I have to use Internet Explorer. For some reason, Java won't work with anything else for me. But if I look at, well, fractions comparing might work on your computer. On mine, it doesn't. It kind of looks like this, and some gray bars right here. I don't know why. This stuff is probably getting outdated, and they need to update it. But if I look at parts of a whole, that's a nice way to see, am I drawing my pieces correctly? So if I divide a circle up into 7 equal pieces, and then look at 4/7 by just clicking on them, I can shade them. That's what 4/7 looks like. If I made it 4/5, that's 5 equal pieces, and there's 4 pieces there. You can see that 4/5 is a much larger fraction. And so if we wanted to make a general rule for this, if we have like a situation like this where the numerators are the same, notice the numerators here are both 4, then we can look at the denominator and say, how many pieces are we dividing a whole up into? On the one on the left, we're dividing up into 5 equal parts. On the one on the right, we're dividing up into 7 equal parts. And it's a good way to start to say, as that number on the bottom gets larger, we're dividing it up more and more into smaller parts. So for instance, if I make this, let's see how large this will go. If I take it out to 30 seconds there, look at how small those pieces are. So 4/32 is going to be even smaller than 4/7 there. And so with the numerators being the same, if I'm comparing two fractions to see which one is larger, then we just look at the denominators. And so you start to think what's left over. And as we subtract fractions, it'll be a little bit easier to see that if I have one whole, that's 5/5, I'm left with 1/5 when I subtract. If I have 4/7, that's 7/7. If I subtract, I get 3/7. But we'll worry about that later on as we start talking about adding and subtracting fractions in the next lesson. Try this one out, 5/6 and 7/8. Which one is larger and which one's smaller? So if you pause the video, all you should be able to do is just draw those two diagrams to kind of look those over. And so I've got a circle divided into pretty close to a 6 there, and another one divided into 8s. I've got 5/6, so it's going to be 5 of them. And then I've got 7/8. And so this fraction right here is going to be the larger fraction. And we can even look at this as it's only an 1/8 away from a whole. So you only have an 1/8 right here. This is a 1/6 away from a whole. So you have 1/6 right here. Once again, comparing these two fractions, since this one is divided up into larger numbers, this is going to be a smaller slice than this one over here, which could be a larger slice because you're only dividing a whole up into 6 pieces. So because you only got a small slice left here, that means that 7/8 is the larger number. Try this one out, 3/8 and 2/9. So there are my representations. 3/8, which shaded in, would look like this. And then 2/9 shaded in would look something like this. So it's obvious that 3/8 is the larger fraction. But without drawing it out, what's our reasoning here? You think I'm dividing this up into 8 pieces and this into 9 pieces. So these pieces are going to be smaller pieces, because I'm taking a whole and I'm dividing up into a lot of pieces compared, well, not a lot of pieces compared, but more pieces compared to this one. So it's going to be smaller. And then I'm only shading in 2 versus 3 here. So I'm shading in fewer pieces also. And so this fraction, 2/9, is going to be a lot smaller than 3/8. There's an algebraic approach to this that you probably are somewhat familiar with from high school, where you got 3/8 and 2/9, and they tell you to put the greater than or the less than symbol on this, or I guess you could include equals as well. And all we're going to do is say, what is 3 times 9? And that's 27. And 8 times 2 is 16, like this. And so since 27 is bigger than 16, 27 must be larger. Well, 27 is larger than 16, so 3/8 must be larger than 2/9. Now, other than just saying, hey, that's the trick to it, I think some students sometimes get confused because they do this, 3/8 and 2/9. They understand there's a trick, but they don't always remember how to apply the trick because they don't understand why the trick works. If we were to do it the wrong way and do this common mistake where they say 3 times 9 is 27 and 2 times 8 is 16, then it looks like 2/9 should be larger than 3/8. And so it's always key to say we're multiplying, we're going to cross multiply these up like that, not down, or you're going to get messed up. But the real thing I want you to know is why this works. And it all goes back to getting a common denominator. So with a common denominator, what we would do is say, what's a number that both 8 and 9 will go into? Well, this is where the last lesson with the least common multiple comes to play. They'll both go into 72. They both go into 72. So I'm going to write down 72. That's my new denominator. What did I multiply 8 by to get 72? I multiplied it by 9. So I got to multiply the top by 9 and I get 27. What do I multiply 9 by to get 72? I multiplied it by 8. So I have to multiply the top by 8 and I get 16. And so these two fractions are equivalent to these two above it. And so now I can compare it a lot easier because they have the same denominator. And with the same denominator, I can see that I'm shading in 27 of these 72 pieces. Over here, I'm only shading in 16 of these 72 pieces. And so this fraction on the left must be larger. And so this little cross trick right here, I'm actually just doing that 9 times 3 and not worry about finding the common denominator. I'm just saying 9 times 3, 8 times 2, and I'm looking at the numerators. And I know that if I made the denominators the same, the numerators would look like that, and I can quickly compare which one's larger. For this class, I want you to be able to explain with words over here and diagrams, but I also want you to know how to do it the quick way algebraically, so you can compare them in a hurry if you need to. Now, let's look at that number line. So it says use reasoning to place these 6 fractions, 4/5, 4/7, 5/6, 7/8, 3/8, and 2/9 on this line, showing their positions relative to each other. Let's go ahead and just make a line. So I just did this, drew a line. We're going from 0 to 1. I want you to do the same. I want you to pause the video and see if you can compare these. If you need to, I'll start you off with the hint. So pause the video if you want to try it without the hint. And so the first thing I'm going to compare, since your first hint here, is look at 4/5 and 4/7. So if I had 4/5 and then I had 4/7, notice they both have the same numerator. Which one's larger? Well, this one's divided into more pieces, so 4/5 should be larger because fifths are larger than sevenths. So I've got 4 of those fifths and only 4/7 there. So if I'm putting these in order, 4/5 and 4/7 go like this. Then I'm going to look at, if you need another hint, 7/8 and 3/8. So let me write those out. I'll do these in a different color just so they separate some. 7/8 and 3/8. Now those two have the same denominator. And so with the same denominator, I know that this one has more shaded in than this one because I only got 3 of the 8ths shaded in here, 7/8 shaded there, so I'm going to switch those two. So if I bring 5/6 in next, I'm just going to look over here and compare it to 7/8 and say which one is larger, 5/6 or 7/8. So think back to those circles there. If I were coloring them in, which one would I have more left over with? So on this one, I would only have, whoops, not the circle. I was thinking circle and clicked on it. On this one, I would have 1/8 of a slice left over if you ate 7/8 of a pizza. On this one, I would have 1/6 left over. And so which one's larger, an 1/8 or a 6? Well, a 6 is larger, which means that this right here is a smaller fraction than this one, because this one only gives you a tiny sliver left. This one gives you a nice good slice of pizza left. So this is a larger fraction. So I know that 5/6 must be less than 7/8. But compare it to 3/8. How is it compared to 3/8? This one is 1/6 left over. This one would not be 1/8, but it would be 5/8 left over. Now 5/8, you're thinking like, how can I compare that 5/8 to the 1/6? I can't visualize that in my head. I like to pick a number that's somewhere in between, and usually it's a half or a fourth. In this case, 5/8 is larger than a half, but 1/6 is not. Or you could look at just the fraction. Everybody looks at these things differently. You could look at this fraction. 3 out of 8 is not equal to a half. It's less than a half, because 4 out of 8 is a half. 5 out of 6 is much larger than a half. So 5/6 falls in between the two green fractions there. It's got to be larger than 3/8. The next fraction I'm going to add to this is 2/9. Now 2/9 I know is less than a half, because if I were writing this fraction in ninths if I took half of 9, it's 4.5. So technically 4.5 over 9 is equal to 1/2, and so 2/9 is less than that. And the reason why I'm thinking that way is it tells me where to go. Is 2/9 closer to this end on this number line, or is it closer to this end down here? And it's going to be closer to this end down here. So I want to start comparing it with these numbers in here. 2/9 and 3/8 is where I'll start off with. And so I want to verify that 2/9 is smaller than 3/8, or verify that 2/9 should be moved, in between over here. So the way I'm going to look at this one is I'm going to say, what if I had the number 3/9, which is bigger than 2/9, and compare it to 3/8? Which one is the larger number there? Well, remember, this is going to be larger slices because you're dividing up that circle into smaller amounts. This one's going to be smaller slices because you're dividing, that denominator is larger. You're dividing the whole into more parts. And so 3/9 is less than 3/8. So if I'm talking about 2/9, that must be even smaller than 3/9, which is smaller than 3/8. And now that I've got that in order, I can start comparing 4/7 and 4/5 and put them in their spots. But first thing I want to do is start putting these kind of on the number line where they go. You could have been doing that the whole time if you wanted to. 2/9 is around 1/4, because I know 2/8 is a fourth. So it's really close to a fourth, but 3/8 come next. 5/6, though, is going to be a little bit further up. In fact, if you wanted to, you could divide this into 6 by saying, let's look at this piece, divide it into thirds, and then dividing that into half. And so you got 1, 2, 3, 4, 5, 6 pieces. So you could say 5/6 is about right there. That's if you want to be a little bit more accurate, but I wouldn't actually keep those lines there, because 3/8 is not equal to 2/6. It becomes a little bit more complicated when you have all these different denominators, but if you just want to see where it goes, that's one way that you could go about it. So 7/8, we've already determined that 7/8 is larger than 5/6, so it can go somewhere in here. Once again, you could kind of divide this out in eighths if you wanted to, but it didn't say it had to be super accurate. We're just trying to compare and order these fractions in their correct spots. And that just leaves us with 4/7 and 4/5. If you want, pause the video right here if you haven't been doing that, and see if you can find out where those go. When I look at 4/7, I say, is 4/7 larger than a half? Well, I know that half of 7 is 3.5. So 3.5 over 7 would be 1/2. 4/7 then is larger than a half. 3/8 is less than a half, because I know 4/8 is a half. So I know that 4/7 goes to the right of 3/8. Then when I compare 4/5 to 5/6, remember that we're going to have leftovers there as far as if we remove them from a circle. So this has 1/5 left over, this has 1/6 left over. 1/6 is smaller than 1/5, so this is more of a fraction that, or more parts of the fraction is going to be shaded in versus the part of the circle being shaded in with 4/5. You can check these by multiplying. 5 times 5 is 25, 6 times 4 is 24. So this is going to be smaller than 5/6. You could do that with any of them. Check them using that cross multiplication technique that we talked about. So I've got these in the right order. The only thing I really like to do left over here is just kind of put them where they should go. I know, like I said, 4/7 is bigger than 1/2, so 1/2 is about right here. I'm going to move 4/7 this way. 3/8 is really close to 1/2. You're only an eighth away from a half, so I'll put it there. 2/9 is pretty close to 1/4. 4/5, 5/6, they're kind of all in the right spot right there. And so that's where I'll put them, and then put in these little lines right here to show where they are. So as far as these problems go, I was going to include this on this video, these types of problems. I think I'm going to hold off on that. We're about at the 30-minute mark, and I know if you've been pausing the video and trying out videos, you and your study time may be at the hour mark. So I'm going to pause there and save the rest for the next day, including why we cannot divide by 0. So it should be posted. You can go ahead and watch it if you got the time today, but I'm going to go ahead and let you take a break, try out some homework problems, and then continue with the next lesson when you are ready for it.